Honors Chemistry, and welcome to 8.7, the last little tidbit from Chapter 8. So, really, 8.7 is just sort of re-emphasizing and adding a little bit more information to the topic we already started in Chapter 3, which is the concept of reactions or processes being exothermic or endothermic. So when we talk about endothermic, it means energy is absorbed, right? Energy is required, right? And usually we are talking about thermal energy, right? So heat has to be absorbed in order for the process to happen, right? So we talked previously, right, about things like melting, right, boiling, and in the context of reactions, right, it's a reaction that requires the input of energy to occur, right? So things like decomposition, right, require energy to put in before the reaction will occur, okay? Exothermic, right? So here we would have processes like freezing, condensation, and if we're talking about reactions, things that are exothermic tend to be things like combustion reactions, neutralization, which is a fancy word for what? Right, that's a fancy word for acid-base double displacement, but those tend to be exothermic, right? So note here, right, you might be a little bit confused because you might think, well, I know that when I start a fire, right, like in a safe, normal kind of way, right, it requires the input of energy, right? Like fires don't often happen without either some sparks or a match or something to get it started. But note that that's different, right? That's called activation energy. That's the amount of energy necessary to get a process started. But once you give it that amount of energy, it will then release energy and happen on its own, yes? So if we think about how starting a fire works, right, you get all your supplies together, right? You have something that is combustible with access to oxygen, and then you input a tiny bit of energy, known as the activation energy, and then the reaction is self-sustaining, right? Whereas in a decomposition reaction, we have to put energy in, and we have to keep putting energy in order for the reaction to keep happening. Yes, does that make sense, right? That's what that distinction is. All right, so just a note here, because we did talk about heat back in Chapter 3, right? Where we could take the mass of something in grams, right? The C value for that thing's in joules per grams times degrees Celsius, and then the temperature change in degrees Celsius. And using all of that, we could solve for Q in units of joules, which is heat, right? And just heat, not heat per something, just heat. So it's a quantity, so I could say that 960 joules of heat are released when something happens. 960 joules of heat are required when something happens, but that when is also going to be tied to whatever amount of substance I used, yes? If I increase the mass, I'm also going to increase the amount of heat, right, or the magnitude anyway of the heat, yes? Does that make sense, right? Whereas here, when we're talking about heat of reaction or enthalpy of reaction, right? It's a conversion factor, right? So this is 960 kilojoules equal to 1 mole of the reaction as written, right? So it's a relationship. Obviously, if I increase my number of moles, I'll increase the amount of heat released. But this is a conversion factor, right? That converts between the amount of reactant or product and then the amount of heat either released or absorbed, right? Whereas heat is just a quantity in and of itself. Yes, does that make sense, right? And that's the differentiation between the two. So if we're looking here and we're doing a problem together, right? So these are your skill builders, right? It says ammonia reacts with oxygen. Calculate the heat associated with the completed reaction of 155 grams of ammonium, right? So we're going to start with our 155 grams of NH3. And as is often the case, we're going to go ahead and turn that into moles, right? So we're going to go with our 17.04 grams of NH3 for every 1 mole of NH3. And then here, right, we're going to take this into account. So what that says is 906 kilojoules of energy are released per mole of reaction. So if I'm looking at the key thing here, right, that's per every 4 moles of NH3. Yes? 906 kilojoules of energy are released for every 4 moles of ammonia. So for every let's fill that in. For every 4 moles of NH3, there are 906 kilojoules released, right? Everything cancels. I've just solved for the amount of energy released with the reaction of 155 grams of ammonia. Yes? All right. What mass of butane in grams is necessary to produce this much? I forgot to superscript that. What mass of CO2 is produced? I didn't format any of this. Okay. So anyway, same principle, right? So I'm looking for mass of butane and I'm given a heat, right? So that's going to be our starting information, right? So 1.5 times 10 to the third kilojoules of heat, right? And then obviously I'm going to have to convert that to, oh, no, because this is already in kilojoules, right? So, and it says produce this amount of heat. So here, making sure that we're being cognizant of our signs, if it's produced, that's negative, yes? Which means that this is negative 2658 kilojoules. And then in my numerator, we're going to tie it to butane. So that's for every 1 mole of C4H10, right? That's what powers those little camper stoves that people take out if they're, going out with those little tiny grills. The big ones that you would use on like a gas grill on your porch, that's typically propane. But anyway, C4H10, and then we know that for every 1 mole of C4H10, we would use its molar mass. So then we have 58.14 grams of C4H10, and then moles cancel, kilojoules cancel, right, and those negatives cancel, and then we have solved for mass of butane necessary to produce that amount of heat. Yes, does it make sense? And then follow-up question is what mass of CO2 is produced, right? And so if we wanted to answer that question, right, we could simply from here, right, add in a couple more steps, right? Actually, no, not from there. From here, right, we could simply add in for every 1 mole of butane, right, there are, where am I? Here. 4 moles of CO2, right, and then for every 1 mole of CO2, 44.01 grams of CO2, right? And that would be the follow-up, where we can take the amount of heat produced, right, and tie that back into other parts of the reaction, right? Or we could even just tie the, there's alternatively, right, we could just take that and then use this number there, right? So in that there are negative 2658 kilojoules for every 4 moles of CO2, right? And then use the molar mass there, right? Either way, it gets the same thing done. Yes, does that make sense? All right, thank you for listening. Be good, and no worries. You'll do some more practice. All right, be good.